Hello and welcome. This is Safa. In this episode, we are not just plotting rotation. We are building the mathematical foundation of 3D orientation. Every line of this code represents a geometric transformation. Okay, section 1 here. First, we define the original vector. I intentionally choose a unit vector along the x-axis. Why? Because in marine robotics, the x-axis usually represents the forward direction of the vehicle. So this vector represents the heading direction of the AUV before any rotation. This is our body reference direction. Okay, and here, section 2. Now we define roll. Roll is rotation about the x-axis. The rotation matrix Rx here comes directly from 3D rotation theory. Notice the first row is 1, 0, 0. That is because when we rotate around x, the x component does not change. Only y and z are affected. This structure is not arbitrary. It comes from projecting the vector onto the yz plane and rotating it there. Okay, section 3. Pitch. Pitch is a rotation about the y-axis. In this case, the y component remains unchanged. That is why the middle row is 0, 1, 0. The x and z components are coupled through sine and cosine. This represents the vehicle tilting up or down. And section 4. U is rotation about the z-axis. Here, z component remains constant. The rotation happens in the xy plane. This is exactly how heading angle works in navigation systems. And RZ here, 0, 0, 1. Okay, section 5. Now we combine the rotation, and this is critical. Rotation order matters. Matrix multiplication is not commutative. So, RZ, RY, RX is not the same as RX, RY, RZ. This order defines the final orientation. Okay, now let's execute the script and observe the geometric effect of each rotation. Run here. Okay. The blue vector is the original heading here, you can see. The red vector show roll. Notice it barely changed because the vector was aligned with x, and the green vector show pitch. Now we see a vertical displacement. The magenta vector represents your rotation in the horizontal plane. And finally here black vector show the full combined orientation. Okay, you can see. Here. Okay, Euler angles gives us an intuitive way to describe orientation, but as systems become more dynamic, we will need more robust representation. This is how we mathematically describe orientation in 3D. And from here, things start to get even more interesting. Okay, thanks for watching.